So we're back again, gang, looking at these different map projections and the purpose of which are selected by whomever is wanting to display whatever the data is they're trying to give you with the least amount of distortion. And so one of the problems that we've had, of course, in American education is using this type of map right here, which is a cylindrical projection which shows you incredible distortion up toward the poles. So the map would only touch the Earth at the equator and get more and more and more distorted as you get to the North and South poles. This is a Mercator projection, and it was made by Gerhardus Mercator 500 years ago, which means it doesn't have royalties anymore, which is why publishers used to put it in textbooks all the time, because they didn't want to have to pay money for a different kind of map that someone else had created. Okay, so some of us got this kind of education. I think they've changed it a good little bit since I was in school, but I certainly remember asking why Greenland wasn't a continent along with South America when I was in grade school. And the answer was, that's not how big Greenland is. Greenland is much smaller. It's a big island, but it isn't a continent. And then we look at run lines of connecting places, but this is how the mariners would use this to plot going from point to point on different sorts of maps, depending on where they're going. So not real useful for the classroom, and certainly brings in a lot of problems. So the great seven most well-known geographic organizations in the United States and Canada came together and said, hey, don't use the Mercator projection anymore, please. It's terrible. It doesn't serve a purpose. In fact, it's counterproductive and makes people see the Earth in an erroneous way. So new map projections, of course, been made. Some are just beautiful works of art. I mean, Buckminster Fuller and the Dymaxon, he laid out the Earth in triangular form, but you know, it would put I don't know, you should look them up. They're really kind of cool. I don't have enough time for this to be a map reading course or any of the sort, but if you look at it, it's neat the way it's all laid out, but it does take a bit for the mind to wrap around looking at a configuration. Like, I don't like this configuration at all. This Gauss-Peter projection meant to smash up the areas of the north and accentuate the areas within the tropics. Now, this would have been done by churches and some governments and whatnot, so they could say, hey, these are where all the poor people live, and they're more important than where the rich few live right up in this area. And that's something that you'll have to consider when you look at maps. Is the person who made the map, the cartographer, did they intend to fool me or influence me in a certain way, or good or bad? And so being able to have a critiquing mind is part of what we're trying to build here. And so that area distortions can occur, that shape distortions can occur, directions, and you know, just the relative size of places changes as well. So this is this Robinson projection right here is kind of the go-to map for most textbooks, it seems to me, and they're used liberally throughout most of my other textbooks from other courses. And I can see why, because this one right here, the peeling of an orange, maybe you've heard of that before. If you'll take it off and flatten it out, and it'll look kind of like this, but of course it'll rip and tear unless you purposely cut it into these sections. But a lot of people don't like looking at the Goode's Homolocene projection because it's interrupted, because it doesn't fill in all the gaps. You got to imagine that this is stitched together and imagine it going into a ball. This is the type of maps that we used in my geography study, though, so I got really used to them, but I get that you'd want this kind of compromise, and this is a good compromise, the Robinson projection is. Now, looking at distance and direction, we need to look at a couple of things here. So, obviously, if you're on the North Pole, everywhere from that point is what? South, okay? As you take off in all these different directions, you're all headed south, but you still have the quadrants of the 0 eastern hemisphere to 180 degrees and 0 western hemisphere to 180 degrees. So want to look at how azimuths and well, I think I've got it here in a moment, but well, let me back up for a second. Back in the day, when cartographers would make their maps, they would put these quite elaborate compass roses. And when they were hand drawn, they did end up looking like flowers. So you'd have the four cardinal directions, then the secondary, and then the tertiary in between, north, northwest, and south, southeast, and such. So you'd always see these things on the maps themselves, showing you direction based on, you know, the four quadrants, if you will. But if we look at azimuths and bearings here, I wanted to touch on this for you, in that both go about the process of direction in a little bit different way, but just wanted to show you the difference. So with 0 being here at the top in north, and then radially counting all the way up to 360, okay? So that your azimuth is telling you a direction, say for instance, north is 0, south is 180, 90, and 270, that's east and west. If you look at bearings, though, they go halfway between. So if you look right down here, so south 45 east, which is that direction right there, is the exact same as saying, all right, that's all the way to 90 degrees plus another 45, right? Because the in-between of 0 and 90 is 45. So the in-between of 90 and 180 is another 45. So that gets you 130 degrees. And that those two things are saying the same thing. So azimuths and bearings, depending on the maps that you're using, you'd want to pay attention to those to know exactly what direction. This would work better for you, if it make more sense if you were in the field and needing to use those on, say, a topographic map. So I'm leaving some stuff out here. There's certainly more room for me to talk about maps, and I probably will at least some a little bit later, because I don't want to wear you out on the first day or the first week. But I do want to hit on a couple other things. As you can see in your textbook, that magnetic north and true north are not the same thing, okay? And in fact, these things are changing all the time. So when we look at these in just a moment, I'm going to show you how the poles wander. But I also want you to know about map basics. There needs to be a title. When was the date of the thing made? What about the date of the data that they used? You probably want that too, if it's a historical map, for instance. That the legend has all the keys to your symbols. That there's potentially a verbal scale, a representative fraction, which would be like 1 over 3,600 or 36,000, something like that. Or even a bar graph where you'd measure a piece of paper against it. The length is, you know, an inch is equal to a mile, or 1,000 miles, okay? And then, of course, directions. And having those is important. But true north and magnetic north are not the same things. And heck, I don't even know why I put this in, but I think I remember learning years ago in the Urals mountains in Russia about Magnitogorsk, meaning magnetic mountain, had a huge iron load in there, and that anybody with a magnetic compass, it would just point it to the mountain. But these things too, that, you know, these creatures are the termite, golly, I don't even know. I should just leave it. I'll leave it alone. Termites are kick ass, though. All right, I'll leave it at that. So, but I promised you magnetic north. And one thing I need you to know too is this: the poles switch. I'm not saying the Earth flips. I'm saying the magnetism flips. And right now, North Pole dominant is what there is. South Pole is not. There's still a magnetic pole, but it's weaker of the two. So we know these have switched over time, and we'll talk more about this when we get into the part of the course about knowing about geology and age of the Earth, the 4.6 billion years of Earth, and being able to read that in the rocks, and we can actually do that. But this wandering pole here, the best one I got was within 2015, but in 1900, it was down here, close to mainland Alaska, not up in the islands, but it's been wandering farther and farther north, and it's gotten pretty close up here, as you can see with the inset map. Okay, so geomagnetism is again, I can't tell you emphatically what magnetism is and what's caused it, but we know it works, with gravity and everything else. So if we look in here at the magnetic pole, it's actually wandered off here off the continent of Antarctica in the south and off here into the ocean. Okay, but one of these, let me tell you about Russia real quick. When everybody was going for their land grabs, everybody decided that even though there's areas of Antarctica that are claimed, no one has true right over them. And it was the Russians that said, all right, we want the true north, or excuse me, true South Pole, but they had already missed it. The Norwegians had already discovered it, Roald Amundsen, and poor Robert Falcon Scott of Robert Falcon Scott. All of his crew died from the British trying to get there, and they lost, and then they got stuck and all froze to death. And then the Russians said, well, hey, we'll, instead of getting true South Pole, we'll get the magnetic pole. But as it turned out, of course, it moves, and so they're Lake Vostok. But they did happen to be over a fresh lake of water underneath Lake Vostok, which went down more than 2 miles deep, I think it says here. And I'm still not sure what their discoveries were, but they wanted to drill into that and see what life was like. The age of the ice is what matters here. And so what was around at the age for that lake, and would they find any unique creatures? Not really sure what turned up on it, though, to be honest with you. So if you're interested, take a gander. So looking at the magnetosphere, it's this is the 24 reversals in the last 5 million years. And what that means, it just keeps flipping and back and forth. So this is the age in millions of years. So, to today, 1, 2, 3, 4, 5 million. And you can count the flips. And how do they really do it? They just look at the rocks, the magnetic portions in there, like iron, that they can look into those portions of the rock and actually see, are they oriented to the north or oriented to the south? And this is easily seen if you take the mid-Atlantic ridge of the Atlantic Ocean, and you can find those, stitch them together exactly, and have that understanding of why, not necessarily why, I guess, but that it flips, and that we can use it to date the Earth and rocks. Okay, so one other last thing is that the Earth's magnetosphere protects us from the solar wind. So that magnetism does keep us from being blown into into nothingness, and it's really kind of cool to see how some of this works. But I don't know it. I'm just introducing it to you. So if you want to take off with it and read more about it, be my guest. That's how you learn about stuff. But I'm going to call it quits here. So I'll come back maybe at some other time and talk about some other types of maps, but I'm going to call this one wrapped up. So hopefully it was what you wanted. Hopefully it wasn't rambling. Hopefully it was informative. And I know it's not the most exciting thing. I wish we were together and you could ask questions and we could take the conversation where we could. But this is learning at a distance, and this is the best I can do. So I hope this finds you well, and I'll see you the next time. Take care. Bye.